Yes, yes,
Yeah. Yeah, sure. Sorry, continue.
yes. So next they've defined the sine of a complex number and the cosine of a complex number.
Mm-hmm.
This they've used like Euler's formula to like derive an expression, and then they've set that expression to be equal they've used that definition. So so
Hmm. Perfect.
it's yeah. So and then they've defined pi to be the I guess infimum of okay. Yeah. So they've defined pi to be the smallest positive real root of sine. So that
Perfect.
is their definition. So if we can, so how Rudin has done it, he's defined pi to be two times the smallest positive root of cosine. But here they've done something
Same.
similar, but
It's the same. That will give the
same
same
thing.
real number, right?
Yeah. So that is how they've defined pi, and then these properties of the exponential function, which can be verified, and that e to the power 0 is 1, which
Right.
again you can verify from here.
Yeah. I mean, okay, I would, yeah, you can verify from here or from this identity. I think it's easier. But anyways,
Yeah, from the identity.
but
Yeah. And then the derivative of e to the power ax, which is a e to the power ax. So all these basic definitions, which like many, I mean, most calculus students should be familiar with.
right.
Now, sine 0 and cos 0, they have just given the
This,
values, and they have shown that sine squared x plus cos squared x is 1. Derivative of sine is cos, and derivative of cos is minus sine. Uh, so, and this inequality, which again, it's quite easy to show. So, if x lies between 0 and 1, then pi x will lie between 0 and pi, and then this inequality follows from there.
right.
Uh, yeah,
So this is fine.
yeah. So this is yeah. Sine pi is 0. Of course, because of this,
Yeah.
pi is the it is by definition 0. So and
Ah,
cos pi is
okay.
-1, which I guess they've used this
Right. Okay.
for cos pi. So proof, they've given the proof,
You have
of
also
course.
given the proof, so you can, no, it's fine. You have told us the proof. Yeah.
Yes, yes. So yeah,
Nice.
right, right. So now so all that is done. Now we consider this following family of functions.
Hmm.
So f sub n x is x power n times 1 minus x to the power n by n factorial.
Mm-hmm.
So as is, there is no motivation to consider it, but they say we consider this function is because it works.
Yeah.
So yeah.
Okay. Yeah, it's fine.
So now lemma 2. So this was lemma 1, all these five properties. So
Mm-hmm.
lemma 2, if uh, if x lies between 0 and 1, then fn lies between 0 and 1 by n factorial. So
Right.
this again I think
It is
is
evident.
very easy to
Yeah.
it's quite easy to see, but proof is here anyway.
Yeah.
Uh, we just if x lies between this and this, then so does 1 minus x, then raise to the nth power, uh, multiply, and uh, then we get this, that the product is between 1 and n. Then we just divide by n factorial. Then we get what we want.
Hmm.
So now they're talking about the integer expand. I mean the expansion of x to the power n, 1 minus x to the power n. So this again just binomial expansion. One can see that this holds true. But it's not. The only thing that we'll be needing is that the CIs are integers and
Hmm.
that this is 2n. So everything
Okay,
else is
not
but
needed.
this is easy to see. Yeah.
Right.
So that is lemma 2. And so lemma 3, so they're using this notation Fn uh and then k in brackets. So that is they're saying is the kth derivative of Fn. Well, yeah, I think it's easy to see that this is infinitely differentiable, so this makes sense for any k.
Hmm.
Uh, and so the first, I think, major claim is that Fn, the kth derivative of Fn at 0 is an integer for all k. So I think that is the first major claim. And so is kth derivative of Fn at 1. So actually, this particular question, the proof of this lemma was actually an ISI question. So this one.
Okay. Nice.
So I
I
remember
don't
it from
remember it,
there.
but
Yeah,
right.
yeah. So there. So and they say so proof. They'll see now we will see why we wrote Fn as a sum. So they're just
Uh,
they expanded out Fn. So this is I guess the first derivative. You can see it's just this, but they're just
yeah.
applying the what's the power rule.
First.
So they do that and they find like these expressions. So and then if we just put x equal to 0 here,
Hmm.
we get 0. We get 0 back. So f1 of x is f1 of 0 is 0, f2 of 0 is again 0,
Yeah,
and
till
so
n
on
minus 1, it will be
all
0.
the way up. Yeah. So for k less than n, the kth derivative of fn at 0 is 0.
Right. And after that, you
Now
have too
if
many
we
coefficients, so it will
now
divide.
put uh, between
Ah, hello.
yeah,
Yes, between.
yes, so it will divide, yeah,
Yes, like when you.
which is what there is as well.
Just 1 second. I think there is.
Between n and 2n.
Cool. Fine. Yeah. And Aryan, can you? Is it possible to
Yes,
maybe make this part occupy a bigger part of the screen? Make the text occupy the bigger part of the
yes,
screen. Like
like
you can remove this side column.
so I didn't understand.
Uh, I'm saying,
Oh, I'm using Chrome, so I don't think I can do.
oh, this side column.
Actually, I can try opening this in Edge browser where it might be
It's
bigger.
it's up to you know. It's not. I think you just click on this plus now besides 100%, and it will become bigger.
Where is that, sir? Where is that?
No, just on just so there's 100%. Page number 4 by
Oh,
7. Next,
okay.
I think
Uh-huh.
just yeah,
Yeah, is
just
this fine?
yes, yeah, it's perfect, right?
Okay.
I hope it is
Yeah,
not too
okay.
big for you. Good.
Uh, actually, no, it's fine. Yes, sir.
Right.
But the thing with Zoom is there's some bar there, so like I think this is better for me, so that way I'm able to read. So is this
Right, I
fine, sir?
understand. Yes, yeah, perfect. That's why I asked
Okay, yes. So they've just so using that they've written it as a sum. So then they just differentiate. So using that
you.
they find expressions, but they plug in x equal to 0. So all the terms
Hmm.
we are only left with terms that have a factor of n factorial in them. So what happens is, so in the numerator, you have something greater than n being taken. You take that factorial. In the denominator, you have n factorial. So that is obviously an integer, where at least when n is a natural number. So that is easy to see. And for k greater than 2n, this
This
will
is itself
obviously
0. Yeah, The function is
Yeah,
0.
it's the zero function itself, so that is done. Uh, so yeah, so we get that for all x, for all real numbers x, we have that the kth derivative of fn of x is 0 if k is greater than 2n. And for k less than or equal to 2n, we have already shown that at 0 it is an integer. And they also fn, the k derivative of fn at 0 is 0 for k less than n. So they've shown that.
Right.
And k derivative of fn of x is 0 for k greater than 2n. They've shown that.
Yes.
So now for part B,
That is just by symmetry of the function.
symmetry of the function, yeah. They
Uh,
just put instead of fn of x, so they replace x by 1 minus x, then differentiate. So if you differentiate this, so you'll get a minus sign pop up. You'll get minus 1 to the power k. It'll come out in the front, but then everything else remains the same, and you have this.
right.
So from part A, we know that this is an integer and that this is 0. Thus, we get the same conclusion for fn, k derivative of fn at 1. So I think
Hmm.
this uh, these two results, they're quite important. But yeah, so we've proven them, and
Yes. And it's quite interesting because it's happening that it's integer for every k, but for different k's, the reasons are different. But eventually
yeah,
it is 0 for every k. Yeah, that's quite,
eventually it is 0. Yes,
yeah.
yeah.
Okay.
So now, so they're saying let a be a real number. So given an epsilon greater than 0, there exists some n greater than 0, such that a power n by n factorial less than epsilon for all n. So this is nothing.
That
It's
we
just the limit.
limit. Yeah.
Yeah. So this is they clarify that. So this is equivalent to showing that this limit is 0. Uh, so
Yeah.
they say, so let a be a real number. We know that e power a is a real number. That again follows just from
Okay.
the definition of e. But e power a is exactly this, which is convergent.
Yeah, it's fine.
Yeah. So then obviously we must have that this term inside must go to 0 because the sum is convergent.
Right.
So that's all.
Hmm.
Uh, now they have just defined rational number. So a real number is called rational if it can be written in this form for integers a, b with b not equal to 0. Otherwise, it's irrational.
Right.
So yeah,
So this
basic.
is fine. Lemma 5 is also fine. It's just, I mean,
Uh,
squaring is the operation which,
yeah, if n squared is irrational, then yeah. So
yeah.
that is fine. So now they prove that pi squared is irrational.
Ah,
So
yes.
this is the main, but it's surprising because uh, so far we only like derived the most basic facts. So one might think, how would you use those uh, like extremely basic facts to show? But
Yeah.
so this is due to Ivan Niven. So
Right. I mean, like, for example,
uh,
right now it's not at all clear that I can prove it from these lemmas so far.
from
I
these,
don't think I can prove it
yes,
from the lemmas. Yeah.
yeah, and the function also it seems to have no link. But
Already. Yeah.
anyway,
Correct.
yeah. So uh, they they uh, they proceed by contradiction. So supposing pi squared is rational, then pi squared is a by b. For so here they've restricted a and b to be positive integers because pi is greater than 0. So either a and b are both positive or a and b are both negative, in which case we replace them by minus a and minus b. And we also know that pi squared is greater than 0, so a itself must be greater than 0. So
Yeah.
uh, without loss of generality, we can just write a and b, where a and b are natural numbers. So
Correct.
that we can do. So then they introduce this quite complicated looking function. So that is b power n times this pi to the power 2n fn of x minus, and so on. So here, if you can see the power of pi, uh, the power of pi is decreasing from 2n to 0. And fn of x, so instead of its power, or we're taking the derivative. So it's,
Right.
I can, I guess you guys can see the pattern. So,
Yeah.
and we also have an alternating sign. So
Hmm.
it's plus for even and minus for where odd. So minus 1 to the power n there. So this
Right.
is what they've done.
Right.
Uh, so yeah, now they note that each factor bn pi to the power 2n minus 2k, that must be an integer. But that is of course because we're assuming pi squared is a by b.
Nice.
So so if we multiply bn throughout, we get this, which should be an integer. They've given an example for bn, multiplying it. Oh no, oh, it's not an example. They've proven it for all k.
General, yeah.
So you can just see
Hmm.
where k varies between 0 to n. I think, yeah, k varies between 0 to n. So because pi varies between 2n, the power of pi varies between 2n to 0.
Correct.
So k varies between 0 and n.
Right.
So they've just simplified this expression and they've shown that you get this, which is of course an integer when k is between 0 and n.
Right. Right. Right.
Oh, right. And also from lemma 3, we know that the kth derivative of fn at 0 and 1 are integers. Thus,
Hmm.
g of 0 and g of 1 are also integers for all k. Again, just sum of integers.
Hmm. Right.
Product of two integers is an integer. Sum of two integers is an integer.
Correct.
Right. And now they're saying that fn is infinitely differentiable. So this claim they haven't proven, but I guess it's
No, you
easy to
told us
see.
in the
And
beginning that it is differentiable for all n.
yeah, yeah.
You were telling, so it's,
So
I mean, it's,
right, right. And
yeah.
g, and since g is just defined as sum, and we know that if the derivative of a function exists, if f and g the derivative exists, then so does f prime plus g prime exist. So using that, we can just say that g of x, it's also differentiable infinitely many times. So what they do now is they consider the second derivative
Right.
of g of x again, but uh, all that we are doing is taking the second derivative of fn, because g is uh,
The
defined in
linear.
terms of n like this.
Hmm.
Yeah. So now, so they've derived this following expression for
Right.
g
Correct.
second derivative of g at x, where of course nothing's happening. It's just that instead of fn, we have second derivative of fn, or 2 plus 2, and so on, like that. So
Right.
now they ask us to consider this sum, pi squared g of x plus second derivative of g of x. So they take the bn common.
Yeah.
So if we add pi squared, uh, this will obviously become
Yeah, and things will cancel
1.
out, right? Yeah, because
Things will cancel out. Yes, yes.
it's translated.
So we have this and we have this. So they're adding pi squared. So yes, it is translated. So everything will cancel out. So except for the first and last one. So almost like a telescoping. Not
Hmm.
strictly, but almost. So pi squared times g of x plus the second derivative of g uh, of x is this, bn plus pi to the power 2n plus 2 fn of x plus minus 1 to the power n fn 2n plus 2 x. But we know from lemma 3 that fn of this 2n plus 2, that derivative at x is 0, since 2n
Correct.
plus 2 is greater than
Yeah,
2n
it's a zero
for
function.
all n.
Yeah.
Zero function. So it reduces to this with very clean looking expression.
Right.
So we have but then I think what they do next is substitute. Yeah, so they substitute pi squared as a by b.
Hmm.
So bn, so bn is a power n by pi to the power 2n. So then they just put that in. So they get pi squared g of x plus second derivative of g of x will give you pi squared a to the power n fn of x.
Right. Yes. Okay.
So that is what they've done. And now they've said let h of x be this thing.
Okay.
Again, there isn't much motivation for any of this, but they say it works, so we take it. So we go with that.
Right.
So h of x is this function, first derivative of g of at x multiplied by sine pi of x minus pi of g of x cos pi of x.
Okay.
Okay. And then they take the derivative of this thing.
Hmm.
So we get uh second derivative again, just
Product rule.
product rule. Yeah. Nothing too complex here. I guess
Yeah.
this one can see easily. So but the interesting thing is this thing which we calculated already comes out. And it's multiplied just by sine pi of x.
Okay.
So
Hmm.
so we've shown that the first derivative of this new function h at x, it'll be pi squared a to the power n fn of x sine pi of x.
Right. Right.
So yeah, uh, this is I think this is pretty easy to see. Then they say using the second fundamental theorem of calculus. So I think now they're integrating it,
Hmm.
and bounds are 0 and 1. Again, this is also, I guess, pretty easy to see. Yeah.
Right. Yeah.
So that will be h of 1 minus h of 0. Just but if you just put h of 1 and h of 0, it's easy. So that be pi g of 1 plus g of 0. Again, we don't know g yet, but it'll be pi g of 1 plus g of 0.
Hmm.
So pi squared times this integral is pi times g of 1 plus g of 0. Then they cancel out the pi, divide by pi. So pi times this integral is g of 1 plus g of 0. But okay, I think this is where the proof we start seeing that somewhere there might be a contradiction coming. So
Okay.
this this integral is the sum of two integers.
Right.
So this integral itself is an integer.
Right. Yes.
But
Yes.
now they introduce the lemma. So
Okay. It's between
we
two
know this.
integers, kind of.
Yes, yes.
Let's see. I mean, okay. So they use the
Yeah,
lemma. Right.
yeah.
First lemma.
So we are almost, this is like the home stretch.
Okay.
So now we have this, which we derived already when x is between 0 and 1, which is certainly true for this. So,
Yes.
so if you multiply this by pi a to the power n, you get this.
And that thing goes
So,
to 0. So if n is large, it cannot be an integer.
yes,
That's,
exactly.
yeah,
So from lemma 1, we also know that sine pi of x
is
is
also
at
less
most
than.
1. Yeah.
Right.
So hence, if we take the integral, we get this strict inequality. Uh, Again, just simplify all of that. But here you get pi a to the power n by n factorial,
Hmm.
which is which then you can cancel out pi if you want, but then you get that this integral, which is strictly greater than 0, it's coming to
Hmm.
be uh, you know is lying between 0 and 1, strictly between 0 and 1, or anything for that matter, because a to the power n by n factorial can be as small as we want. Or
Nice.
what we can do is we can,
Hmm.
yeah. So for large enough n, we just have this. So it's strictly between two integers.
Right.
So
That
we have an
is
integer 0 and 1, which is a contradiction.
right. And what are the references?
Oh, okay. So
Okay,
they have
these three.
mentioned, yeah, this Herntzien's book only, Abstract Algebra.
Hmm.
But I wanted to use this because they've sort of like explained it uh, a bit
Hmm.
more.
Right. So
So yeah,
yeah, that's nice. Yeah, so that was a nice presentation, right? Yeah.
yeah.
And
But
Sejan, yes.
yeah, just one might on if one were to read it, they would like there's almost no motivation for G, H, F, but I don't know how he came up with it, but
Yeah, I don't
he
know
did
that.
so.
Yeah.
Yeah.
So are there any question? Is there any question about the proof? Anything which is no?
I think I have to go through the proof once again because there is so much lemmas and all these
But you
things.
can
So,
maybe you can if there is any thing which is not clear, you can ask it now. That should be
no,
fine.
I mean,
Okay.
no, I don't have any problem with the proof, but there is so much thing to remember, so I just have to go through.
Right. Fine. Fine. Yeah, I mean these proofs, like I mean, the more you see these proofs and do them, it's then it becomes like gradually, yeah, natural. But yeah, it's a tricky proof. But yeah, then have a look at it. It's so you can share. What is the title of this? Maybe
Yes, sir. So this is a detailed proof of the irrationality of pi
why
by
by Niven?
Matthew. Yeah,
Oh,
so proof is by Niven, but the article is written by Matthew Straw
right,
or
right.
something. The
Okay,
bar is blocking, so I don't know what it is, but
okay. Matthew Strong.
Matthew Straw, Matthew Straw. Yeah.
Fine. So this is a good this thing. So maybe we should just thank him because it was a complete presentation. And
Yes, yes.
okay, but have you looked at the proof in Hurstein abstract algebra?
Yeah,
At
it's exactly the same as this, sir.
it is the same. Okay, then it is.
Yeah, yeah.
Then we have to find a better proof. Better proof in the sense, you see, the point that is happening is like you're defining. So here they are defining this pi in a certain way through a very specific trigonometric polynomial. So it seems like there are a lot of things that one can possibly do next, right? It's not clear what is there is no canonical next step. There are many steps that
Yes,
one
yes.
can take, and so what Niven takes a step, and so it looks very clever. I mean, I suppose it is clever if he doesn't have a underlying theory, whatever it is. But the point here is that there are too many choices at every step, right? So what I feel is that if we instead go about looking at pi in a certain class of numbers, okay, if you view pi as a member of certain family of numbers, then maybe it will be the proof can become more canonical, right? Feel that
Yes, yeah, yeah,
because
yes, I.
then it will follow from the structure of the family. But coming up with that family, I do not know. Is there some theory or I don't know. Yeah, I really do not. Yeah, because this proof is good certainly, but let me just have a look at Hurstein abstract algebra. I don't know. We don't, I think, have much time before it ends. So I'm just, yeah. Can you just go to the proof
Oh,
where
so
the proof?
this is topics in algebra. Pi
No,
is
this will
not
not
there.
have.
Here,
I'll just
yeah.
share my screen 1 second. Yeah,
Okay, okay. So I'll stop sharing.
yeah. So I think here I think I have. Oh God, I don't have. Hurst. Because I mean, if Hurston provides a proof which Where is it? Yeah, which uses some properties of pi, but having a proper definition. The irrationality of pi. Okay, is it visible? Okay, so we just have 2 minutes, so we will not be able to do much. But after this, you can present the transcendence of E. We would love to
Okay.
hear that.
Yes. Yes.
But
Yes.
let's
Yes.
just look at this. Yeah, it is the same proof. First year calculus course. It's yeah. It's just that he doesn't divide it into lemmas. Yeah, it has no. As you're right. I mean, it's just shorter, but it's just there's nothing different.
Yes. Yes.
Uh,
I
mhm.
guess why they at least undergraduate texts, why they go for Niven's proof if they even include it, is because any other proof, it I guess it has more presupposes more knowledge. I guess I don't know, but
Yeah, I suppose so. I mean, there has to be some more definitions and things to make things look
yeah.
simpler, more canonical.
Right.
Oh no. Maybe what we can do is I mean, we can try to read this Loivel's criteria, right? Maybe this can throw some insight. I don't know. Correct? Maybe next time it's a very small proof. So, Srijani, would you like to just tell us about this next time? This Loivel's criteria? Since
Yes,
I have read this
I
at some
think
point.
I have gone through some Lively's criteria or Lively's theorem from the book What is Mathematics?
Okay, then might be same. There is a
My
Loivel's theorem.
undergraduate.
So maybe next time you can just, it's a very short proof. So just, 1/2 you can just tell.
Okay,
It
okay.
might not be related to this. It might actually help us to
I think
understand that
it is related to something transcendental
transcendence. So
number.
then maybe next time you can prove transcendence of pi after that. That will be the next thing,
Okay.
right? Yeah. So anyways, let's then meet after some time, some minutes, and then we'll see the transcendence of E. Okay.
Yes.
Okay.
Yes.
Right, but we have to think about this better proof of pi. Otherwise, this proof is nice, but it should, tell us something more.
There is one. So there is one that uses the expansion of tan x, but
Yeah, that will also be trick based, I think, right? I mean,
yeah, it's
ev-
trick based. Yeah.
everything. Yeah, okay. Let's see. Okay.